Hello everyone, in this video we're going to explore topic 10.4, the intro test for convergence. Alright, let's talk about the theorem. Suppose the function f(s) is positive, continuous, and decreasing. These three guys extremely important. Okay, you must have these three guys happen in order to apply this theorem, right? On the interval k to infinity, where k is a positive integer greater than or equal to 1, and ls equal a sub n. Right? Number 1. If the interval from k to infinity of ls ds is convergent, so is the series. Number 2. If the interval from k to infinity of ls ds is divergent, so is the series, right? The integral test will always result in having to evaluate an improper integrals, which you learn in topic 6.13. The AP Calculus BC exam has required students to state the conditions for which the integral test can be applied. You typically will not have to prove they apply, rather just state that they apply. Alright. Now I'm going to rule the first one. If the interval from k to infinity of ls ds is convergent, so is this series, right? Now you look at this function right here, it's going to be decreasing, right? It's continuous, right? And it's positive because it's above the x-axis, right? Now I'm going to use the right endpoint remain sum. We have this point right here is the height of the rectangle. It's going to be f of 2. And this guy actually a sub 2, right? This guy is f of 3. And this guy actually a sub 3, right? This guy f of n. And this guy actually a sub n, right? So the error equals the error of each rectangle, and then you add them up, right? So you know that each rectangle has the width of 1, right? So you have 1 times f of 2, right? Plus 1 times f of 3 plus etc. plus 1 times f of n, right? And then I just replace f of 2 with a sub 2, right? And then multiply by 1 is going to be itself, right? So it can be a sub 2 plus a sub 3 plus etc. plus a sub n, right? And this guy actually the series of a sub k when k goes from 2 to n, right? This guy actually less than the error under the curve. And the error under the curve is defined as the interval from 1 to n of f of s ds, right? Since this one is a decreasing function, the right endpoint remain sum always underestimates the error, right? Now suppose the interval from 1 to infinity of f of s ds converges. It means limit of the interval from 1 to b of f of s ds when b approaches infinity equals a constant. I call this m, right? Now since f of s is positive, right? We have the interval from 1 to n of f of s ds always less than the interval from 1 to infinity of f of s ds, right? Observe that this series right here is less than this one, right? But this one less than this one, right? So by transitive property, we have Now look at this series. It's gonna start from 2, right? But we need this series to start from 1, right? So we're gonna add a sub 1 both sides, right? So we have the series a sub k when k goes from 1 to n less than the interval from 1 to infinity of f of s ds plus a sub 1, right? Now look at this one right here. This guy converges to m, right? So if you add a constant, it still converges, right? So I call this one as capital N, right? Now I'm gonna name this one as S sub n, right? So I have S sub n always less than or equal to S sub n plus A sub n plus 1, right? Because I just add a constant to the series right here. And it's gonna be the series A sub k when k goes from 1 to n plus a sub n plus 1, right? And it's gonna be the series a sub k when k goes from 1 to n plus 1, right? And it's gonna be s sub n plus 1, right? So we just prove that s sub n less than or equal to s sub n plus 1, right? It tells us that S sub n converges. So the series A sub n when n goes from 1 to infinity is also convergence, right? And the first one has been proved, right? Now let's prove the second one. In order to prove the second one, we're gonna use left endpoint remain sum. Now similarly, we have the error equals the width times the height. The height in this situation is going to be f of 1, right? Plus 1 times f of 2 plus etc. plus 1 times f of n minus 1, right? And you know that this guy actually a sub 1. This is a sub 2. This is a sub 3. And this one a sub n minus 1, right? So it could be a sub 1 plus a sub 2 plus etc. plus a sub n minus 1, right? And this guy actually the series of a sub k when k goes from 1 to n minus 1, right? And this guy always greater than the interval from 1 to n minus 1 f of s ds, which is the error under the curve, right? Right? Because we're going to use the left endpoint remain sum on the decreasing function. It's going to be overestimating the error under the curve, right? Now suppose the interval from 1 to infinity of f of s ds is divergent. It tells us that the interval from 1 to n of f of s ds approaches infinity if n approaches infinity, right? And since f of s is positive, right? We can conclude that n minus 1 always approaches infinity, right? So the interval from 1 to n minus 1 of f of s ds approaches infinity, right? Now let's call this one as s sub n minus 1, right? So we have s sub n minus 1 equals series a sub k, k equals 1 to n minus 1, right? Now we're going to add both sides by an, right? So it turns out to be S sub n equals the series A sub k when k goes from 1 to n, right? This guy greater than the interval from 1 to n minus 1 of f of s dx plus a sub n, right? So we can conclude that the partial sum s sub n is divergent, right? Then the series a sub n when n equals 1 to infinity also divergent, right? And it's good time to stop. Thank you for watching. I hope you enjoyed the video. Remember that if you failing to prepare, you're preparing to fail.
We rise like tall buildings as the chemicals they take us higher. The night's young and it's just begun as she puts her hand in mine.